Okay, so the next topic we're going to talk about is differentiability. So before we talk about differentiability, we need to review what continuous meant. So remember, there were three parts to the definition. The limit existed, the function value existed, and the limit value was the same as the function value. So continuous, we want to basically realize it's using the original function is defined, okay? So those are the same. What happens on differentiable? Differentiable is kind of a root word of derive, derivative, and so it's similar concepts, but with the derivative function, not the original function. So differentiable, first of all, is going to utilize the derivative function. So a function is differentiable at a specific x value. They let that be c, just like we did with a for limits, if the derivative exists. So that's what I say. Continuous means, can you plug in a value to the original function and get it? Differentiable means, can I take the derivative and then substitute that value and get a value? That's part of it. The same idea with the left and right limit is the same idea with the left and right derivative. So we want those derivative values to be smooth or a continuous change in derivative values. So as long as you can take the derivative and plug it in, it typically will be differentiable. If there are certain graphs that have sharp points, cusps, vertical tangents that are not differentiable. So like if they give you a graph and we had the absolute value, or if I was given another graph like this, see, and my sides are curved. That's what a cusp is. That's a sharp point. So those are not differentiable. So the graphs are continuous because the original function is defined, but the slope values on like the left and the right, they are a dramatic jump. Like these are all negative, these are all positive, and they didn't just smoothly go that way, like on a parabola. Let's look at a parabola. If I would do my tangent lines, they gradually change from negative to positive. So that's why I say smooth, okay? Vertical tangents are really hard to see, but you can have a graph like this. Okay, and so technically there would be one quick value that has a vertical tangent, okay? But when you go to do their algebraic derivative, you will see that on these two functions. The absolute value is always tricky, so beware of that anytime anyway. That's the idea, okay? So let's get some rules and to really formalize the differences. So we use a big D for differentiable and we use a big C for continuous or continuity, okay? So this says a function is differentiable, then it must be continuous. So if I tell you, like in the directions, that a function is differentiable, it automatically implies that the function is also continuous. If you can find the derivative values, you're going to be able to find the original values, okay? So that's why. Second, if a function is continuous, it doesn't mean it's going to be differentiable. Remember, I can plug in all the original values of x and get a value, but when I go to take the derivative, maybe I can't. So like, let's see an example of that. What if I was given f of x equals the square root of x? Well, let's say cubed root. Sorry. So if I have the cubed root of x, I can take cubed roots of negatives, cubed roots of positives, and the cubed roots of 0. So that is continuity, okay? But if we take the derivative, well, that would be x to the 1/3. So f prime of x equals 1/3 x to the negative 2/3, which is 1/3 x to the 2/3. And if I plug in 0, then that makes my denominator 0, which means I now can't have a slope value when x equals 0. So that's why I can plug in 0 in the original, but when I take my derivative, I'm actually not able to plug in the derivative, and that makes it not differentiable at x equals 0. See the difference? Okay, the last one says if a function is not continuous, then it can't be differentiable either. Well, that should make sense. If I can't plug in an x value on the original, when I go to take the derivative, you typically can't do that either, okay? And there's lots of examples. Radicals are like the easiest. Like if I had 1 over, let's just say it was the cubed root of x, on the original, well, I can't plug in 0 here. And when you go to do the derivative, you're going to still keep a cubed root in the denominator. I was just going to be to a different power, and you're not going to be able to plug in 0 there either. So that's the idea. Okay, so next, we're going to be given some graphs and some functions. So I want to know if it is continuous, differentiable, neither, or both. Okay? All right, so let's talk about it. So, and typically they want it to be at this break. So they have given us a specific value. If they don't, like on I, J, K, and L, that means it is for all values. But on these graphs, when they give you that special value, they only want you to identify it at that value. Okay, so just know that about the homework too. So at 3, we actually have jump discontinuity. That was from Unit 1. So this is, if it's not continuous, remember it's going to be nothing else. So you always want to start with continuity. So we're going to say that that's neither. Okay. Let's look at B. We have a hole there, so that's removable discontinuity. So once again, that's not continuous, so it won't be anything else either. All right, let's look at C. At 0, that function is defined. And then if we look at the slope values, well, they do all smoothly continue, and it's a smooth curve. So you don't even have to do the tangent lines for the derivative. So this is going to be both. All right, let's look at 0. Well, it's continuous because there's no holes. So I'm going to make a little note. Let's look at differentiable. So what I want to look for not differentiable is a sharp point. And it's hard to tell, but there is kind of a little sharp point there because this is a line. So all of those slope values would be the same. And then we abruptly change. So this one is not differentiable. So we're going to stop at continuous. All right, let's look at E. That line, remember, that's an imaginary vertical asymptote. So there is a break there. That's infinite discontinuity. So this is neither. All right, F, that would be an absolute value equation. It is continuous, but because of that sharp point, it's not differentiable. So we're only going to say continuous. All right, well, let's look at G. G is continuous because there's no holes, but we kind of have a sharp point there. Okay, see, it's not a smooth point. So that one is going to be continuous. And H is kind of tricky. So at -1, it is continuous, but there is a brief vertical asymptote. It is really, really hard for you to identify, so just be aware of that. So this one is also continuous because I had a vertical asymptote, so it's not differentiable there. When you go to take the derivative, it would be an undefined slope. Okay, so let's look at I. When you're given the functions, I actually think it's easier because I just do them and then I think about it. So if I look at the original, can I plug in all the values I want to and get something? Well, yeah, it's just a quadratic. So it's definitely continuous. For differentiable, I'm going to actually take my derivative and ask the same question. Can I plug in any number I want into the derivative and get a value? Yeah, that's just a line. So definitely. So this one's going to be both. Okay. On J, you always want to be leery when you see squared over a linear term for factoring. So they want us to factor x minus 4, x plus 3. And so really, I'm still on my original. I am supposed to reduce that. This is going to give us the shape. And then remember the term that reduces, that gives you a hole, which means we have a hole in the graph at x equals -3. So it's not continuous, which means it can't be differentiable either. So this is neither. All right, K. Well, I can take the sine of any angle. It's a sine wave. It keeps going. Okay, that was terrible. So it's definitely continuous. The derivative is cosine. Well, that has a sinusoidal wave as well, with no holes. So that's differentiable. So this is both. All right, the last one. Well, if I plug in 0, I'm going to have a hole. So this is neither. It's not continuous at all. So I don't even have to do the derivative. Okay. And typically when you have a fraction, there should be some type of discontinuity, because that's when your undefined values happen on the original or on the derivative. All right, so on a piecewise function, we did this before with continuity. So you want the two y values to match at the break. So it's going to be the same idea. You want the y values on the original to match. And for differentiable, you want the derivative values or slope values to match, okay, from the left and the right. So it says, once again, determine whether the function is continuous, differentiable, neither, or both of the piecewise functions. So let's talk about continuity, and I'm just going to label it. So for continuity, I'm going to use the original. So I need to plug in the x value and see what we get. Even though it's not equal, remember, I could have an open hole or a closed hole, but we want them to meet up and be the same. So on the top, we get what? 2 squared minus 12 plus 10. So 4 times 14. 14 minus 12 is 2. And on the denominator, the second part, 4 minus 2 is 2. So since these y values are the same, it is continuous. So for differentiable, we want to take the derivatives. We get 2x minus 6, and we get negative 1. So on the bottom part, this is my slope. And it's a slope when x equals 2. So if I substitute 4, I get 4 minus 2, which is negative 2. So no. So all we know is it's continuous. All right. So let's try. If we substitute negative 1, and negative 1 here. Let's see, we get 1 minus 4 is negative 3. What's that? 1 minus 4 is negative 3. So that's definitely continuous. For differentiable, we've got 2x plus 1, and we have negative 1. So it's when x equals negative 1. I mean, technically those are still there. So if x is negative 1, we get what? Negative 2 plus 1 is negative 1. And so our derivative values are also the same. So this is continuous and differentiable. So we're going to say both. And I'm going to write this one over here, continuous. All right, our third example, same idea. 4 is our critical value. So root 4 plus 5 is 9. So I get, I'm going to draw it this way, root 4, which is 3. And then 4 minus 4 is 0. The cube root is 0, 0. And then I get 4. So this one is not continuous. So that means that it is neither. I don't even have to check the derivatives. If it's not continuous, it cannot be differentiable. Now, on the last question, these could be free response or multiple choice, but it says find the values of a and b that make f of x differentiable. So what's going to happen is, because we have two parts and we know it's differentiable, it means that our derivatives are equal. But differentiable implies that it's also continuous. So that means that our y values on the original function are equal. And so you're going to end up with a system of equations to solve. Okay, so first I'm going to set up continuous. So I know that ax squared plus 1 has to be the same y value as bx minus 3. And we know that that's when x is equal to 1. So we can substitute. So if x is 1, we get a plus 1 must equal b minus 3. And I think this was on a free response, but it was only for continuity. Now, we also know, and we can leave that there, we also know that the function needs to be differentiable. So I'm going to take the derivatives. So I have 2a, because remember that's just a number, so you would multiply by the power, and then subtract 1. The 1 derivative goes to 0. And the derivative of bx, like if that was 5x, would just be 5. So this derivative is just b. And once again, we know that that's when x equals 1. So I can substitute x equals 1. So 2a equals b. And so now we have a system of equations. This one is really set up for substitution. So instead of b, I can substitute 2a. So we know a plus 1 equals 2a minus 3, and then we solve this for a. Subtract a, add 3, and so a equals 4. And since a equals 4, that means that b equals 2 times a, so b equals 8. Okay? Notice that all they said was that f of x was differentiable. So you had to remember that that also implies continuity and solve a system. All right, we're just going to try another one. So continuity, I know ax cubed plus 1 has to equal b, x minus 3 squared plus 10. And we know that x is 2. So 8a plus 1. 2 minus 3 is negative 1. Squared is 1, so b plus 10. And then we know the differentiable, so we're going to take the derivative. So we got 3ax squared. The 1 goes to 0. And this would be a chain rule. So I'm going to bring the 2 down, so 2 times b. The inside stays the same. Subtract 1, and then the derivative of x minus 3 is just 1. The derivative of 10 is 0. And we also know that it's at x equals 2. So x equals 2, I get 4, so 12a, x equals 2. 2 minus 3 is negative 1 times 2, so negative 2b, and I'm going to divide by 2. So negative 2, sorry, equals, divide by negative 2, so negative 6a. And so once again, this is also kind of set up. We know both of these, and it's set up for substitution pretty nicely. So 8a plus 1 equals negative 6a plus 10. Add 6a, subtract 1. So a equals 9 over 14. I know it scares people when you get fractions, but you're in a calculus. So b equals negative 6 times a. So divide by 2. So b equals negative 27 over 7. Okay. And there we go. So you go ahead and give it a try and see how you do.